Last time we have done this problem. Another example. Find the moment of the 100 lb force about point O. So here in this figure, we have a force applied on arm OA, and we want to calculate the moment about O. So to remind you, the first step when we want to find the moment of a force about a certain point is to consider the line of action of the force, and we draw the perpendicular from O to the line of action of F. Then we can say first that the magnitude of the moment will be equal to this distance d times the force F. Okay? Now, in this figure, d is equal to 24 cosine 60. And what about the sense of rotation?
Clockwise.
Clockwise, very good, because if you try to do like this, so this force is tending to rotate in this direction about O, so it's a clockwise moment. Okay, so we can simply say here that the moment M is equal to 120 Newton meter, and we put close to it the direction by just putting an arrow in the clockwise direction. Now, the second question, what should be the magnitude of a horizontal force applied at A which creates the same moment about O? So we need to keep the same moment, but now instead of applying a vertical force, we need to apply a horizontal force. What will happen when we do the horizontal force? What will change?
The distance.
Exactly, the distance. So now I draw the line of action of the force, and I take the perpendicular from O towards this line of action. Okay, I have this perpendicular distance is 24 sine 60, and then I multiply 24 sine 60 times F should give me 120. I can get what should be the horizontal force FH times 24 sine 60 should give me 120. I can find what is the magnitude of this force. Now, question C. What is the smallest force applied at A which creates the same moment about O? Who can tell me what condition will give me the smallest force?
Biggest distance.
Exactly, biggest distance. And how can I obtain the biggest projection? Look, what I am doing is I am doing F times D sine of an angle theta. Okay? Sine of theta will be maximum if theta is equal to what? To 90 degrees. So when my force is perpendicular to the arm, what will happen is that I don't need to do any projection because already the whole length OA is the projection. Okay? So the maximum value of the projected distance will be the distance itself, OA. So if I apply a force perpendicularly to my arm, then the moment will be just F times OA without sine of anything because it's sine of 90, which is 1. Okay? So in this case, I will have the minimum force and the maximum arm. Okay? So I can say here that this corresponds to the minimum F minimum times 24 is equal to 120, and I can find the value of F minimum. The last question, at what distance from O a 240 lb vertical force must act to create the same moment about O? So here I have already a force of 100 lb acting at 24 inch from O. So if I want to apply a vertical force, but the vertical force now should be higher, should be 240, but I should still have the same moment. Who can tell me in a quick way what should be this distance? If this is 240 here, what should be this distance? Think about it in a proportional way. So look, I have in the first scenario, I have 100 times 24 cosine of 60 is equal to, in the second case, what do I have? I have 240 instead of 100. I have a distance d that I should find times cosine 60. So you have a certain,
Well,
it's
D will be
inversely
10.
proportional. Exactly, it's 10. It's inversely proportional. If I multiply f by 2.4, I should divide the distance by 2.4. So from proportion, because they are inversely proportional, then the distance here will be 10. Okay, because here I have 100 times 24. So since I multiply 100 by 2.4, I should divide 24 by 2.4 instead in order to get the same number at the end. Okay, so I can verify this from the equation, or I can say directly that they are inversely proportional, and I can say that the ratio of forces is inversely proportional to the ratio of distances, and then it is equal, this distance is equal to. Any question on this problem? Okay, so let us start another one. Now, Now we will define the cross product. Okay? What is the cross product of two vectors? If I have two vectors A and B, their cross product A vectorial B is a vector first. Okay? So in comparison with the dot product will give me a scalar. The vectorial product will give me a vector. Now we will see why we are defining the vectorial product, because it's very important in the calculation of moments in 3 dimensions. Okay. Now, what is the magnitude of the vectorial product? It's magnitude of A times magnitude of B times sine the angle between A and B. Okay. So in cross product, in dot product, it was AB cosine theta. In vectorial product, it is AB sine theta. And now, what about the direction? Vector C has a direction that is perpendicular to the plane containing A and B, such that the direction of C is determined by the right hand rule. How we do the right hand rule in this case? You can see here the figure of the right hand. Okay, what you do is you take the 4 fingers of your right hand, you take them first along the first vector, which is A. You put them along A, and then you curl your fingers towards vector B. Okay? When you do this curling, your thumb will point in the direction of C. So as you can see here, your thumb is pointing upward. So vector C will be perpendicular to the plane of A and B and will be directed up. Okay? So this is how we determine the direction of vector C. And now we can say that vector C can be defined as AB sine theta, which is its magnitude, times unit vector of C, which is the vector perpendicular to plane plane of vectors A and B, and given by the right hand rule. Now, some properties to know about vectorial products. First, it's not like numbers. P vectorial Q is different than Q vectorial P. It's the opposite. It's minus. Why? What will change? If you go back to your figure here, the magnitude will stay the same, but if you inverse A, then if you do the right hand rule, C will be downward. Okay? So if I have the same vector A but opposite, then C will be downward with same magnitude. Okay? So this is why we can say that P vectorial Q is minus Q vectorial P. Now, if we multiply P vectorial Q by a certain scalar A, we can take the scalar or with the first vector, or with the second vector, or we can put it at the end because it's a number. So for the number, you can put it wherever you want. It will not change anything. Now, in case I have P vectorial Q plus S, I can do the development as in numbers. So it's P vectorial Q plus P vectorial S. And finally, if I have, when I have brackets and vectorial product, I should respect the order, okay? Because P vectorial Q vectorial S is different than doing P vectorial Q vectorial S. So whenever I have brackets and vectorial product, I should respect the order done, given, okay? Now, how to calculate vectorial product in a frame if I have ijk. So here, these rules, we will learn an easy method to directly find them. Of course, if I have I vectorial I, it will give me 0. Why? Because by definition, when I have a vectorial product, the magnitude is the magnitude of the first vector times the magnitude of the second vector times sine the angle in between. But here the angle in between I and I is 0. So when I do a vector vectorial itself, it will give me 0. Now, if I do j vectorial I, for example, always I can go always back to the right hand rule. Okay, so if I in this figure I did I vectorial j, because look, I curled my fingers of the right hand from I towards j, so this will give me I vectorial j, and as you can see my thumb is pointing upward in the direction, so I vectorial j is equal to k vector. Okay, and of course, as I can verify this in magnitude and in direction, because the magnitude of I vectorial j is 1 and the magnitude of k is 1, and concerning the sense, it's given by the right hand rule. Now if I take the opposite, g vectorial I, then if I try to curl my hand from g towards I, you will see that your thumb will point downward. So in this case, you will have j vectorial I equals to minus k. I can repeat this procedure for several combinations of vectors, and I will obtain the result. So j vectorial j is 0, for example. K vectorial j is minus I. Now, in order to not do every time the right-hand rule, we come up with a simple method that will simplify things. What you can do is you can draw a circle, simply a circle, and you put on this circle I, vector I, followed by vector j, followed by vector k, and the positive direction is the one turning from I towards j towards k. So this is the positive direction of rotation. What do I mean by the positive direction? If I tell you what is I vectorial j, to go from I to j, you are going in the positive direction, so it will give you plus k. Okay? If you do a j vectorial I, then you are going in the negative direction, it will give you minus k. If you try all these combinations, this circle will allow you to find them without doing the right hand rule. So for example, k vectorial I is plus j. K vectorial j is minus I. Okay? Any question on this?
Doctor,
Yes?
does the right hand rule of the three fingers work here?
Yes, it works. You can do this. You can put your first finger along, if you have IJ, okay, and you want to do I vectorial j, you put the first finger of your hand along I, the second finger of your right hand along j, then the thumb will point in the third direction. Okay, so here, try it. If you do it, your thumb will point upward. Okay, so both methods
Okay.
work. Both method works, yes.
Thank you.
Welcome. Okay. Now, how to calculate the vectorial product in an analytical way. Okay, so you know that vectors are defined by their components. So if I have a vectorial b, then vector a can be written as axi plus ayj plus azk, and the same for b, bxi plus byj plus bzk. Okay, now if I want to do the vectorial product, what will happen? I will expand term by term. Okay, it's like if I multiply numbers. So I start ax bx times I vectorial I vectorial I is 0. So it's I can put I can يعني, I can neglect this, it's 0. Now I continue ax by times I vectorial j. I vectorial j is plus k, so I have here I put ax by times k. Now the final expansion for axi times bzk, I vectorial k is minus j, so you can see it here. It's minus ax bzj. Now I do the same thing for the other terms, so ayj times bxi, j vectorial I is what? If you remember the circle, ji is opposing ij, so it's minus k. So you can see here it's minus ay bx along k. Now if I continue, j vectorial j is 0, and j vectorial k, jk, it's in the positive direction, so plus I, so plus ay bzi. Okay, I continue till the end, and what I will end with is the following expression here. Okay, I have, if I rearrange my terms, I take I components together, j components together, k components together, I get the following. Aybz minus azby along I, minus axbz minus azbx along j, and plus axby minus aybx along k. Now, when they did this expansion, they said we can come up with a simple technique to calculate the vectorial product. And the following technique is illustrated here. I can put the vectorial product in a matrix form. Okay, I put my matrix. I have the first column will be ijk. The second one, the first line, I mean. The second line will be ax, ay, az. And the third line will be bx, by, bz. Okay? And then what I do, I put positive sign above I, negative sign above j, and positive sign above k. And now I first start to find the component along I. What I do is I drop the first line and I drop the first column. What are the remaining numbers? These ones, these four. Okay? So I do its plus, I do a y times bz. So I do this like nx, I do nx between them. So it's ay bz minus b az by. This is the result you can get here. Okay? Then for j, first, I have a minus above j. So the first step, I put a minus when I want to find the number of j. I put a minus, and then I drop this line. I drop this column, and I drop this line. What are the remaining numbers? Ax bz. So I do ax bz minus az bx. And this is what I have here. This is the number I have here along j. And finally, along k, this is a plus. I drop this line, I drop this column. What will remain is ax by minus ay bx. So I get this number. Okay, and that's it. So this is a method to calculate the vectorial product without having to remember this. Now, in general, sometimes if the vectors are not are simple, and if I have, for example, we will do it in examples. If I have like this 2i, for example, 2i vectorial 3j. Of course, I will not use the matrix. I do I vectorial j is k, and it's 6k, and I stop. But if I have three components for the first vector and three components for the second, instead of doing the expansion, the matrix is easy. Okay? Now, let us see how we will use to gather the vectorial product. The vectorial product is very important in calculation of moment in 3D. In 2D, no need for the vectorial product because we have developed a method. We do the projection, the projected distance on the force, and we can determine the sense from the right-hand rule. But in 3D, this is more complex. Okay, we can demonstrate together that the vectorial product of R vectorial F will give us the moment in 3D. Let us see how. If you consider here the following figure, you have a force F. This force F is passing by a certain point A, and I want to determine what is the moment of F about point O. Okay, and we will see together that if I do OA, which is the vector position from point O about which I want to do the moment, to any point of the line of action of F, if I do OA vectorial F, I will get the moment. Why? We will demonstrate it together. First, let us do it together, okay? Let us try to do the previous method, the right-hand rule, in order to determine the moment of this force about. What should we do? This is the line of action of the force. So I take, this is the line of action of the force. I take the perpendicular from O towards this line of action. This distance d is calculated from r sine this angle, sine theta. And theta represents the angle between OA and the line of action of the force F. Okay? So in magnitude, MO is R times F times sine theta, where R sine theta is the distance, the perpendicular distance from O to F, which is called the moment on. Okay? And concerning the direction, from the right-hand rule, I can find that it is pointing up. Now you will tell me why then I need to use the vectorial product if I can do this method. Because you will see that in 3D, it is very difficult sometimes to find the projected distance from a point to a line. And if you remember in math, when you did in 3D, how to project, how to find the distance from a point to a line, it's complex. Okay, so here it is much easier to work with the vectorial formulation. Now, why the vectorial formulation will give me this result? Because look, let us do R vectorial F. What is the definition of R vectorial F? If I do R vectorial F in magnitude, it is magnitude of R times magnitude of F times sine of the angle in between. Okay, so I get RF sine theta, which is F. If I take R with sine theta, what do I get? I get D. So this is the definition of the magnitude of the moment, F times the projected distance. This is why I made sure here that R vectorial F will give me first the same magnitude as the moment. Now, concerning the direction and sense, if I do, in order here to find the direction of moment, I did the right hand rule. Okay, and also if I want to do R vectorial F direction, I will do the right hand rule. I will take my right hand and I will curl my fingers from from vector R towards vector F, and I will get that M is pointing upward perpendicular to the plane of R and F. So also this gave me the same result of the moment. From here, I can say that R vectorial F will give me the vector moment directly. Okay? Any question on this? Now, how to calculate then? As we have seen, we can use the matrix method for calculation of the vectorial product. So if I want to calculate the moment of a force, I can do the following matrix, and in the first line I put ijk, in the second line I put the components of the position vector, or x, or y, or z, and in the third line I will put the components of the force fx, fy, and fc. Let us consider the following example. The rectangular plate is hinged at A and B and supported by a cable which passes over a frictionless hook at E. The tension in the cable is 1349 Newton. Find the moment about coordinate axis of the force exerted by the cable at point C. So here, they gave us the force in the cable in magnitude, and they want us to find what is the moment of this force about the coordinate axis x, y, and z. When they ask for the components of moment about x, y, and z, all I have to do is to do sum of moment about O. Because when I do sum of moment about point O, I will obtain a vector having three components, I, j, k. The component of the vector along I will be the moment of the force about x-axis passing by O, and the component along j will be the moment about y-axis passing by O, and finally the component along k will be the moment about the axis. Okay? So the technique here, in order to find the moment about the three axes, is simply to say, I will find the moment of this force about point O. So I will do, what can I do here? What is the method? It's R vectorial F, okay, R vectorial the tension. What is R? R is the vector position, okay? And the position vector, you can take it from O towards any point on the line of action of the force. And I will demonstrate for you why. If you go back to the definition here, here we did OA vectorial F, but try to take any other point. So if I take, for example, B on F, on the line of action of F, let's say this is B, okay? So let's say here I have B. If I do OB vectorial F, why I will obtain the same result? Because what will change here, what will change is the angle theta here. It's in not another angle, and R will also change. But will R sine theta change? Wherever is my point, R sine theta will always give me what? Will give me always D. Okay? So try also another point. If you try the point here, for example, this will be theta, this will be R, but when you do R sine theta, also you will get the same result, which is D. So the position vector can be any vector joining the point about which I want to do the moment to any point of the line of action of the force. Okay? So let us go back to the problem here. You can choose what you want. For the tension TCE, it passes by C and it passes by E. So you can do or OC vectorial the tension or OE vectorial the tension. So what you should do, you select the easiest point. The easiest point is C because it only has coordinate along Z. Okay? So we have here the coordinates of C are 0, 0, and 2.25. Okay? So now I can say that the moment vector M is equal to OC vector, of course, OC vectorial what? Vectorial the tension vector T. So let me put the vector, the arrow. So it's OC vectorial T. Now how to find T, guys? How to find the vector T? Okay, it's T directed from C towards E. So it is T, C, E. Okay, which method I will use to find the vector T here?
Isn't it the magnitude of t multiplied by its unit vector?
Exactly. It's the magnitude of T times unit vector of CE. Okay? So I can write that TCE vector is the magnitude, which is 1349 times unit vector of CE. Okay? And in order to find unit vector of CE, I need the coordinates of C and the coordinates of E. So if I look at my figure here, to find the coordinates of E, what do I have? I have first along X, it's 0.9. I have along Y, it is 1.5. And no component along Z. So I can put here 0.9, 0.9, 1.5, and 0. And in this way, I am done with the coordinates of E. So now I can find unit vector of CE, okay, which is I take x of E minus x of C, so it's 0.9 I plus 1.5 J and minus 2.25 K. And I should not forget to divide by what? To divide by radical of 0.9 square plus 1.5 square plus 2.25 square. And then I multiply by the tension in the cable and I get the vector TCE. And for vector OC, it's simply, I have the coordinates of C, so vector OC is just 2.25K. So now let us see it here, it will be clearer for you. So the first step, as we said, I find vector OC, then I find vector tension. Now, once I obtain the two vectors, so this is OC and this is vector F, here I have two methods. Or I do the expansion of vectorial product, or I do the matrix method. I will do both for you. If we take first the matrix method, I put ijk. The second line is the vector position, 0, 0, 2.25. And the third line is vector FC. So now, to do the calculation, first, along I put a plus, and I drop this column and this line. So it's plus 0 times this number, so it's 0, minus 710 times 2.25. Okay, so here you get the component along I. Then we move to get the component along J. We put a minus above J, okay? And then what we do is we drop this line and this column. We have these four numbers that will remain, so it's 0 minus 426 times 2.25. So as you can see here, I put the minus before it, and I do the product, and I get the component along J in this way. And finally, for the component along K, I drop this line and this column, and then I will get 0 minus 0, then I get 0. Okay? So this is how I calculated the moment about O. Who can tell me why I can expect that the component along Z will be 0?
Because it intersects with the OC.
Yes, very good, because the force is passing by the axis. Okay, so, and we said that if a force passes by an axis, it cannot produce any moment about this axis. Okay. Now we will do together the second method. If you don't want to use the matrix method, you can say that I want to do directly the expansion. So I have vector OC is 2.25k, and I want to do it vectorial vector F, which is 426i plus 710j and minus 1065k. Okay, so now if I do the expansion, I start to do k vectorial I go back to my circle. Okay, look, you can do it in your mind. I, j, k, I. When I go from k to I am going in the positive direction, so it's plus. So plus 2.25 times 426 along j. Then k vectorial j, when I go to my circle, jk is positive, so kj is negative. So minus 2.25 times 710 along I. And finally, along k vectorial k is 0. Okay, so I got the same result I did previously. Okay. Any question on this? Okay. Now, how to project a vector moment on a certain axis. So we will learn here how to find the moment about any axis we want. Okay. So if we consider a pipe, uh, and the pipe lies in the horizontal plane and it's subjected to a vertical force of 20 Newton. Okay, and we want to find the moment of this force about point O. What we can do is we can just apply the vectorial product. So I take a vector position from starting from the point O towards any point on the force. So here the easiest point is A because I know its coordinates. So to find the moment of the force about O, all I have to do is RA vectorial F. Now, what are the coordinates of RA? I have, if I look at my figure, I can see in my figure coordinates of point A. It has a component of 0.4 along Y and 0.3 along X. So vector RA is simply 0.3i plus 0.4j. And then I do vectorial the force. Since my force is vertical downward, then it is along minus k. So my vector F is minus 20k. And now, if I do the expansion, I have I vectorial k. I vectorial k is negative because k vectorial I is positive in the circle. So I have minus, and I already have minus, so it will give me plus 6j. And then 0.4j vectorial minus 20k. J vectorial k is plus I, but I have a minus, so it will give me minus 8i. So as a result, the moment vector is minus 8i plus 6j. Now, in this example, I started with this example to tell you that if I want to find the projection, the moment about x axis, what will be the moment about x axis here? If the moment about O, yes, exactly. This component minus 8 is the moment about x-axis passing by O, and 6 represents the moment about y-axis passing